So good afternoon. So I welcome all of you for the last module, that is module 5 of fluid pressure and its measurement. So here in this module, we will work out some complex problems and also the problems that have been asked in the recent GATE examinations. So the number is given in continuation of the examples we had discussed in the previous modules. So this is example 14. So you can see the figure. We have a closed container which contains oil, and above oil there is air space, and we have a U-tube manometer. This is the right limb and this is the left limb. So the right limb is kept open to atmosphere and the left limb is connected to the air space in the container, and it is required to find the pressure at the gauge point A. So wherein a pressure gauge, a mechanical pressure gauge is attached. So you are asked to find out the pressure at the gauge point at the bottom of the vessel in kilogram force per centimeter square as well as in kilonewton per meter square. So the depth of oil in the vessel is 3.25 meters. So first let us express all pressures in terms of equivalent column of oil of specific gravity 0.75. There is oil which is stored in the vessel. So the U-tube measures the pressure exerted by air overlying the oil. So because the left limb of the U-tube manometer is connected to that space. Now to start with, initially the levels of mercury in the two limbs of the manometer will be same, but once the left limb is connected to the gauge point or the point in the vessel where air is placed, you can see the level of mercury in the right limb has gone down. That means the pressure of air is below atmospheric. So here the atmospheric pressure has driven the mercury column down in the right limb, and accordingly the mercury column in the left limb has risen up. So the difference in mercury columns in the two limbs is indicative of the pressure of air inside the container which is overlying the oil. So the pressure of air is below atmospheric or gauge negative. So the magnitude of negative pressure exerted by air is 0.25 meter of mercury. That is the deflection of mercury in the two limbs of the U-tube manometer. So this can be expressed. This 0.25 meter of mercury can be expressed in equivalent column of oil of specific gravity 0.75. That is using the expression, say S oil into H oil is equal to S M, that is specific gravity of mercury, into column of mercury. So here column of mercury HM is 0.25 meter. Specific gravity of mercury is 13.6. Specific gravity of oil is 0.75. So we can get the pressure in equivalent column of oil. That is, so minus sign indicates the pressure is negative, that is below atmospheric, therefore minus 0.25 into 13.6 divided by 0.75, we get the pressure, the negative pressure in equivalent column of oil, that is minus 4.533 meters of oil. Therefore pressure head at A is equal to negative pressure head due to overlying air column plus, so when you go down the pressure increases, so plus pressure head due to oil column of 3.25 meters. So let the pressure intensity at point A be represented as PA. So we have PA is equal to gamma oil multiplied by HA. So 0.75 multiplied by specific weight of water will give you the specific weight of oil into minus 1.283 meters. That is, so already we have at the surface of oil the pressure is minus 4.533 meters of oil. Then you are adding this 3.25, so that becomes 1.283 minus 1.283 meters of oil. So you get the pressure intensity at point A is again negative, that is minus 9439.6 Newton per meter square. So again, if you want to put it in kilogram force per centimeter square, so 1 Newton you have to divide by 9.81 in order to get it in kilogram force, and 1 meter square can be expressed as 100 centimeter square, so that comes to 0.0962 kilogram force per centimeter square. This minus sign indicates that the pressure is negative. So the pressure at the gauge point A is negative. So let us go to the next example. So again, we have a tank that is a twin tank system. So this is the left hand tank, and this is the left hand tank, and this is the right hand tank. The air pressure is minus 0.23 meters of mercury. So the air that is overlying the oil of specific gravity 0.8 in the left tank is minus 0.23 meter of mercury. Determine the elevation of the gauge liquid in the right hand column at A if the liquid in the right hand tank is water. So in the left hand tank you have oil of specific gravity 0.8, in the right hand tank you have water of specific gravity 1. So now let us express all pressures in as intensity of pressure, there is a Newton per meter square. So pressure head due to air overlying oil in the left hand tank, that is 0.23 meters of mercury. So pressure head due to air which is overlying oil in the left hand tank is minus 0.23 meters, that is negative pressure, minus 0.23 meters of mercury. So let the pressure intensity due to this pressure head of minus 0.23 meters of mercury be represented as PD. It is PD, it is at the surface of oil, which is not atmospheric, it is under negative pressure. So PD is equal to gamma m Hm, where gamma m is the specific weight of mercury, that is 133416 Newton per meter cube. Hm is the equivalent column of mercury to exert a pressure intensity of PD, that is minus 0.23 meters of mercury. So the pressure intensity at D will be, that is at the surface of oil in the left hand tank, will be minus 30685.7 Newton per meter square. Now let us come to the gauge point B. The point B in the left limb of the manometer. So pressure intensity at point B will be pressure intensity at point D, that is at the surface marking point D, plus pressure intensity due to column of oil between D and B. So here at D the level is 105 meters, at B the level is 100 meters. So the column of oil between D and B will be 5 meters, 105 minus 100, that is 5 meters. So therefore PB you can find out as this much, 8554.3 Newton per meter square. So that becomes positive now. Then pressure intensity at A. So that is A, pressure intensity at B. Again A is located below B. In fact, the level of liquid of specific gravity 1.6 in the right limb of the U-tube manometer A is below the surface of the liquid in the left limb of the manometer. So pressure intensity at point B, pressure intensity at point B plus pressure intensity due to column of liquid of specific gravity 1.6. So let this vertical depth be y, that is from B to A let it be y. Then PA will be equal to PB plus gamma liquid, that is liquid of specific gravity 1.6 multiplied by y. That is the difference in level of liquid of specific gravity 1.6 between B and A. So y here is, this one, y is not known. Then pressure intensity at C will be, so you are going up from A to C, therefore the pressure drops. So it is PA, pressure intensity at A minus, so you have from A to C, you have column of water. So express that as intensity of pressure, there is gamma W multiplied by HW, where HW is the column of water from A to C. So that will be minus 9810 specific weight of water multiplied by Y plus 102 minus 100. That is 102 minus 100. So you get this much. So solving this, you get Y is equal to 5.3798 meters. So pressure exerted by air overlying water column in right hand tank is 2.06 into 10 power 4 Newton per meter square. So that is given. So pressure of air overlying the water in the right hand tank is given as 2.06 into 10 power 4 Newton per meter square. Therefore, Y can be determined. Hence, elevation of gauge liquid or specific gravity 1.6 in the right hand column at A is equal to elevation of point B minus Y, that is 94.6202 meters. Okay. So let us go to the next example, example number 16. So neglecting the friction between the piston A and the gas tank, find the gauge reading at B in meters of water. Assuming gas and air to be of constant specific weight and equal to 5.501 Newton per meter cube and 12.267 Newton per meter cube respectively. Now pressure intensity at the base of the piston. So that will be weight of piston divided by area of piston. So weight of piston, it is given, that is 15.7 meganewtons. So 15.7 to 10 power 6 newtons divided by area of the piston. The piston is having a circular area, therefore pi by 4 into the diameter of the piston is 110 meters, therefore you get this much. 1651.4 Newton per meter square is the uniform pressure intensity at the base of the piston. So pressure intensity at bottom of gas tank will be pressure intensity at base of piston plus pressure intensity due to the gas column of 100 meters. So pressure due to gas column of 100 meters is specific weight of gas multiplied by height of column of gas, that is 5.501 Newton per meter cube is the specific weight of gas multiplied by 100 meters, so you get 550.1 Newton per meter square. So pressure intensity at bottom of gas tank is equal to 1651.4 Newton per meter square plus 550.1 Newton per meter square, you get 2201.5 Newton per meter square. That is pressure intensity at the bottom of gas tank is equal to pressure intensity at the base of piston plus pressure intensity due to 100 meters column of gas. Then pressure intensity at B will be pressure intensity at bottom of gas tank minus you have the gas specific weight as 5.501 Newton per meter cube multiplied by 2.5 meters is the difference in level between the bottom of the tank wherein the gas is placed and the point B. So that comes to 2187.8 Newton per meter square. Now equivalent column of water corresponding to this pressure intensity is given by the pressure intensity divided by specific weight of water. So you get 0.223 meters of water. So another example, Bourdon gauges are commonly used to measure pressure. The mechanical gauges which are used to measure pressure are Bourdon gauges. So when such a gauge is attached to the closed water tank as shown in figure, the gauge reads 34.472 kilonewton per meter square. What is the absolute air pressure in the tank? Assume standard atmospheric pressure as 101.348 kilonewton per meter square. Now you take the air overlying the water in the closed tank. This is the closed tank. So you have water column and the air overlying the water column. The water surface is under the pressure exerted by the overlying air. So water is subjected to the pressure exerted by the overlying air. The point in the closed tank where the connection for the Bourdon's gauge is made is located at depth 0.4, this is in inches, 6 inches plus 12 inches. So that comes to 0.457 meters below the surface of water in the tank. .457 below the surface of water in the tank. Now pressure at the connection point of the gauge to the tank will be pressure due to air overlying the water column plus pressure due to column of water equivalent to 0.457 meters. So that comes to pressure of air plus, this is 9810 Newton per meter cube multiplied by 0.457 meters, so this much. The center of the pressure gauge is located at a vertical distance of 6 inches, that is 0.152 meters above the connection point of the gauge to the tank. So the center of the pressure gauge, this is 6 inches, that is 0.152 meters above the connection point to the gauge of the gauge to the tank. So pressure at the center of the Bourdon's gauge will be pressure at the connection point of the gauge to the tank, that is this point, minus pressure due to column of water of height 6 inches. So that comes to P air plus 4483.2 Newton per meter square. So when you go up, the pressure decreases. So minus pressure due to column of water of height 6 inches, that is 0.152 meters. So minus gamma W into 1.152. So that comes to ultimately P air plus 2992.1 Newton per meter square. Now pressure indicated by the Bourdon's gauge is 34.472 kilonewton per meter square. Therefore, equating 1 and 2, we have this much. So 34.472 kilonewtons is expressed as Newton per meter square. So multiply by 1000. So 34472 Newton per meter square. So ultimately you get the absolute pressure in the tank will be, so this is the gauge pressure of air in the tank, that is gauge positive. If you want to express the air pressure in absolute terms, that is atmospheric pressure plus the gauge pressure of air, that is 101348 Newton per meter square is the atmospheric pressure, and this is the gauge pressure of air. So that comes to 132828 Newton per meter square. So let us go to the next problem. So this is a problem that has been asked in GATE 2004 with 1 point. So you have an inclined manometer shown in the figure. The reservoir is large. Its surface may be assumed to remain at a fixed elevation. Now A is connected to a gas pipeline. So this point is connected to a gas pipeline, and the deflection noted on the inclined glass tube, right? This is the inclined glass tube, is 100 millimeters, So the deflection, that is the inclined length, 100 millimeters. Assuming theta equal to 30 degrees, that is the angle of inclination which the inclined manometer, the limb of the manometer makes with the horizontal, that is 30 degrees, and the manometric fluid is oil with specific gravity 0.86. You are asked to find out the pressure at A. So you are given 4 options. You have to choose the correct option. So let us work out and find out what is the pressure at A. Now the surface of oil inside the reservoir is under pressure due to pressure of gas in the pipeline. See, this is not a free surface. The surface of oil inside the tank is not a free surface because the pressure is not atmospheric. It is connected to a gas pipeline, so wherein the gas is under pressure, and therefore the oil surface inside the reservoir is under pressure. The surface of oil inside the reservoir coincides with the takeoff point of the inclined manometer from the reservoir. So the deflection of oil along the length of the inclined manometer is 100 millimeters, this inclined length. As the manometer makes an angle theta equal to 30 degrees with the horizontal, corresponding vertical deflection of oil will be 100 sine 30, is it not? So this is 100 millimeters, this is 100 millimeters, and this is 30 degrees. So I want the corresponding vertical deflection. So this will be 100 sine 30, because sine 30 will be opposite by hypotenuse. So hypotenuse is 100 millimeters. So opposite will be 100 sine 30. So that is 50 millimeters of oil or 0.05 meter of oil. So the vertical distance between B and C will be 50 millimeters. This distance will be 50 millimeters. Now what is pressure at B? Now this end of the manometer is open to atmosphere, therefore the pressure that is acting at the free surface of oil in the inclined limb will be atmospheric. So that is 0. So we are expressing the pressure in as gauge pressure. That means we take the atmospheric pressure as the datum. When we take the atmospheric pressure as the datum, it is considered as 0. So pressure at C will be pressure at B plus pressure due to vertical column of 0.05 meter of oil as specific gravity 0.686. So 0 plus gamma oil into HBC, that is gamma oil will be specific gravity of oil multiplied by specific weight of water. So 0.86 multiplied by 9810 Newton per meter cube into 0.05 meter is the vertical component of the deflection. So that comes to 421.8 Newton per meter square. So equivalent column of water required to exert a pressure of this can be determined as, so that comes to 0.043 millimeters or 43 millimeters. So the correct option will be the correct option is 43 millimeters of water. 43 millimeters of water. So you're asked to find out the pressure at A in terms of equivalent column of water. So it is 43 millimeters of water. Positive. This is gauge pressure. This is gauge positive. Gauge positive. So example 19 in the afternoon session, GATE 2017 with 2 marks. So the figure shows a U-tube having a square cross section 5 millimeters by 5 millimeters filled with mercury of specific gravity 13.6 up to a height of 20 centimeters in each limb open to atmosphere. If 5 centimeter cube of water is added to the right limb, the new height in centimeters up to 2 decimal places of mercury in the left limb will be. So initially, see A and A dash are in the same horizontal plane, and the height of mercury in each of the 2 limbs, that is left limb as well as right limb, is 20 centimeters. Now if you are adding 5 centimeter cube of water to the right limb, so 5 centimeter cube of water is added to the right limb, what will happen? So because of the pressure exerted by this 5 centimeter cube volume of water which is added to the right limb, the mercury level here will go down, and correspondingly the mercury level in the left limb will go above A. So here the mercury level will come down below A prime, and here the mercury level will go up above A. So you are asked to find out what will be the new height in centimeters of mercury in the left limb. So it will be higher than 20 centimeters. So let us find out how much it is. Now if you take the cross section of limbs of U-tube, that is 5 millimeters square, therefore 25 millimeters square. So convert it into meter square. 1 millimeter is 1 by 1000 meter or 0.001 meter. So that comes to 0. Followed by 4 zeros, 25 meters square. Now volume of added to the right limb is 5 centimeter cube. You put it in meter cube, it comes to 0. You have 5 zeros followed by 5. 0, 0, 0, 0, 0, 5 meter cube. So what is the corresponding column of water that will stand above the mercury column of 20 centimeter in the right limb will be volume of water added to the right limb divided by cross section area. It will give the height of water standing above mercury in the right limb. So the height of water column standing above mercury column in the right limb will exert a pressure. So this column of water which is standing above the mercury in the right limb will exert a pressure on the mercury surface. So the pressure exerted due to a column of 0.2 meter of water is gamma WHW. So gamma W is specific weight of water, 9810 Newton per meter cube, multiplied by 0.2 meters of water, you get 1962 Newton per meter square. So due to this pressure exerted by water column at the interface of underlying mercury and overlying water here, right? This is 0.2 meter of water. So because of the pressure that is 1962 Newton per meter square, exerted on the interface of underlying mercury and overlying water in the right limb, the mercury column will be pushed down, this will be pushed down, and accordingly the mercury level here will rise up. So what happened, the mercury level will become, so here instead of 20, this will become, say, it goes down by y, so this becomes 0.2 meter minus y here, and here it becomes 0.2 meter plus y correspondingly in the left limb. So 0.2 minus y meters. Correspondingly, due to continuum of fluid, the mercury column in the left limb will be pushed up compared to the original level. That is, the mercury column in the left limb will rise by y meters. So the column of mercury in the left limb will be 0.2 plus y as shown in the figure. Now in figure below, now originally it was A prime. A prime has come down to B by y meters due to the pressure of the overlying water. Now the total column of water is 0.2 meters. So this is 0.2 minus y. Point B in the right limb marks the interface of the new interface of overlying water column and underlying mercury column, and point C is a new level taken by mercury, that is the free surface of mercury column where the pressure is atmospheric. Now let us write the manometric equation for the above figure. Let us express all pressures in gauge units, that is, let us consider the atmospheric pressure as 0 when you are taking atmospheric pressure as the datum and expressing all the pressures in gauge units either as gauge positive or gauge negative depending upon the circumstances. So pressure at C, this is exposed to atmosphere, that is 0. So pressure at A will be more than C because A is below C. The pressure increases in the downward direction. So pressure at C plus pressure due to column CA of mercury. The mercury column has gone up by y meters. So PA will be equal to PZ plus gamma m HCA, that is 0 plus 133416 multiplied by y meters, so Newton per meter square. Then pressure at B dash. B dash is nothing but the point in the same horizontal plane as that of P. B is the new surface of mercury and overlying mercury is the water column. So PB prime will be equal to PA plus gamma m into HAB prime. HAB prime again will be y meters of mercury. Y meters of mercury. So that will be, you get this much, 266,832 y Newton per meter square. So pressure at B will be equal to pressure at B prime because both B and B prime lie in the same horizontal plane. So PB is equal to B prime, that is 266,832 y Newton per meter square. And pressure at D will be pressure at B minus pressure due to 0.2 meters of water. That is this one. From B to D you are moving up, so pressure decreases, so minus. At D is exposed to atmosphere, so the pressure at the surface of water is atmospheric in the right limb at D. So PD is equal to 0. So PD is equal to 0, that is equal to PB minus gamma W because you have water in the column BD. So gamma W into HBD, the column of water from B to D, that is HBD. So PB is 266,832 y Newton per meter square minus specific weight of water multiplied by 0.2 meters. So that comes to, ultimately when you solve for y, it becomes 0.00735 meter, that is 0.735 centimeters. So the new height of mercury in the left limb of the U2 manometer has gone up from 20 centimeters to 20.735 centimeters. The level of mercury in the right limb has come down by the same amount, that is 0.735 centimeters. So example 20, so this has been asked in GATE 24 in the last year in the first session. It's question number 38. A 5 meter by 5 meter closed tank of 10 meter height contains water and oil. This one, this tank on the right side. It is a square tank of cross section area 5 meter by 5 meter. So the total height is 10 meters, that is contains water and oil. So oil is overlying water, is connected to an overhead reservoir that is on the left side as shown in the figure. So let us take the specific weight of water as 10 kilonewton per meter cube and the specific gravity of oil is 0.8. So you are asked to find the total force in kilonewtons due to pressure on the side PQR on the side of the tank. Now, so this is a closed tank containing oil of specific gravity 0.8 to a depth of 4 meters of specific weight, specific gravity 0.8 and to a depth of 4 meters over water of specific weight 10 kilonewton per meter cube and depth 6 meters. So you have 4 meters depth of oil overlying 6 meters depth of water. The surface of oil marked by RR, this is RR, this is PP, PP, QR, R, QP. Okay. The surface of oil marked by RR, this one, in the figure is under pressure as the tank surface is closed. It's a closed tank and oil is in touch with the surface of the tank, top surface of the tank and under the influence of water in the overhead reservoir ABBA. So AA marks the free surface of water in the overhead reservoir. Total depth of water in the overhead reservoir is 10 meters, of which 8 meter stands over the point C, which is connected to the closed tank at D. This is C, which is connected to the closed tank at D. As the closed tank is connected to the overhead reservoir, there is continuum in the interconnected liquids in both the closed tank and the overhead reservoir. So this is the closed tank and this is the overhead reservoir. From the figure, the base BB of the overhead reservoir, is in line in the same horizontal plane with the interface QQ. This is the interface of water and oil in the closed tank. Now pressure at the base BB of the overhead water tank, overhead water reservoir. Pressure at the base, this is BB, this is AA. PB is equal to P atmospheric plus the pressure due to 8 meters column of liquid. To 10 meters, pressure due to 10 meters column of liquid. So that comes to 100,000 Newton per meter square. Now the pressure at the surface RR of the closed tank be PRR. Now the pressure at the interface of the overlying oil column and the underlying water column, that is QQ. PQQ is equal to PRR plus pressure due to column of oil, that is 4 meters. So that will be PRR plus pressure due to 4 meters column of liquid is this much, 0.8 multiplied by 10,000 into 4. So that comes to PRR plus. Now as the base BB of the overhead reservoir is in the same horizontal plane as that of the interface of the overlying oil column and the underlying water column, that is QQ. Because of the continuity, pressure at the base of the overhead reservoir should be equal to pressure at QQ. So let us equate. Pressure at BB is equal to 100,000 Newton per meter square. Pressure at QQ we have expressed, that is PRR plus. So you will get the value of PRR. So PRR will be, this is at the top of the closed tank, will be 68,000 Newton per meter square. If you put it in kilopascals, it will be 68 kilopascals. So pressure at the interface of the overlying oil column and the underlying water column, that is PQQ, is equal to, again you go back to this equation, and you will be getting PQQ is equal to 100,000 Newton per meter square. That is to validate that the pressure at QQ is the same as the pressure at BB, because both are in the same plane. Both surfaces are in the same plane. Now pressure at the base BP of the closed tank, PP of the closed tank, will be PQQ plus gamma W into HQP. That is 4 meters. Sorry, HQP will be. So let us draw the pressure distribution diagram for determining the total pressure exerted on the vertical phase RQP of the closed tank. Sorry, this will be P. This is P and this is R. I'm sorry. This is P, this is R. So this is PR. PR is equal to 68 kilopascals. PQ is equal to 100 kilopascals. And PP, that is PQQ plus pressure due to column of water of 6 meters height. So that comes to 160 kilopascals. So now the pressure distribution diagram for determining the total pressure exerted on the vertical phase RQP of the closed tank can be done. So it is required to find the pressure force on the vertical phase RQP of the closed tank of size 5 meters by 5 meters. The dimension of the vertical phase RQP in the direction perpendicular to the plane of the paper is 5 meters. So the magnitude of the total pressure force acting on normal to the vertical phase RQP of the closed tank will be area of the pressure distribution diagram multiplied by dimension of the tank perpendicular to the plane of the paper. So dimension of the tank perpendicular to the plane of the paper is 5 meters. So what is the area of this pressure distribution diagram? So area of the pressure distribution diagram will be, you have to find out the area of this figure. So that is given here, and the total pressure force comes to this much, 5580 kilonewtons. So pressure at Q will be felt throughout as a uniform pressure distribution, and you have the triangular pressure distribution due to the column of water here. Now let us go to the next problem, which has been asked in GATE 2018 in the second set, that is afternoon session, with 2 marks. A closed tank contains 0.5 meter thick layer of mercury at the bottom. A 2 meter thick layer of water lies over the mercury layer. A 3 meter thick layer of oil lies above the water layer. So first at the bottom, 0.5 meter of mercury layer, and over the 0.5 meter of mercury layer you have 2 meters thick of water layer, and over the water layer you have 3 meters of oil or specific gravity 0.6. The space above the oil layer contains air under pressure, so you have air under pressure. The gauge pressure at the bottom of the tank is given 196.2 kilonewton per meter square. The density of water is 1000 kilogram per meter cube, mass density. Acceleration due to gravity is this much. The value of pressure in the airspace is 4 options are given. You have to find out the correct option. So the problem statement has been represented in the form of a figure here. So AA represents the surface of oil which is subjected to pressure by the overlying air in the closed tank, wherein we want the pressure. BB represents the interface of overlying oil and underlying water, this one. And CC represents the interface of overlying water underlying mercury, and DD represents the base of the tank. So specific weight of water will be mass density of water multiplied by acceleration to gravity. So 1000 into multiplied by 9.81, you get 9810 Newton per meter cube. Specific weight of oil will be specific gravity of oil multiplied by specific weight of water, that is 5886 Newton per meter cube. Specific weight of mercury will be 13.6 is the specific gravity of mercury multiplied by 9810, you get 133416 Newton per meter cube. Now pressure at DD will be 196.2 kilonewton per meter square, that is given in the problem. So in Newton per meter square. The pressure at CC, so when you are going up, the pressure decreases. So pressure at DD minus pressure due to 0.5 meter column of mercury, it is this much. Pressure at BB will be pressure at C minus pressure due to 2 meter column of water, you get this much. Then pressure at A, that is surface of oil, which is under pressure due to the air overlying it. So pressure at BB minus pressure due to 3 meter column of oil and specific weight, this much. So you get 92.214 kiloliter per meter square is the pressure in the air space. That is the pressure, the air pressure exerted at the surface of oil in the tank. So the correct option is this one, A. So this is again another problem asked in GATE 2023 in the afternoon session, set 2 with 1 mark. The pressure in a pipe at X, say the center line of the pipe, is to be measured by an open manometer as shown in figure. Fluid A is oil, so you have two fluids. Fluid A is oil with a specific gravity of 0.8. That is the oil which is flowing through the pipeline, say. And fluid B, that is the manometric liquid, is mercury with a specific gravity of 13.6. Find the absolute pressure at X in kiloliter per meter square. Assume density of water as 1000 kilogram per meter cube and acceleration due to gravity 9.81 meter per second square, and atmospheric pressure as this much, 101.3 kilonewton per meter square. The fluid at A, that is fluid A is oil or specific gravity 0.8. Specific gravity of mercury is 13.6. Mass density of water 1000 kilogram per meter cube. Acceleration to gravity 9.81 meter per second square. So specific weight of water will be mass density of water multiplied by G, that is 9810 Newton per meter cube. Atmospheric pressure is given 101.3 kilonewton per meter square. So you get Newton per meter square. So you are asked to find out the pressure in the center line of the pipe, Px. So now, say point C, C prime and C double prime are in the same plane. So pressure at C will be equal to pressure at C prime equal to pressure at C double prime. As points X and X prime are in the same horizontal plane, pressure at X will be equal to pressure at X prime. Then pressure at C will be pressure at X prime minus, because you are going up from X prime to C, so the pressure drops, minus pressure due to column X prime C of fluid A of, or there is oil or specific gravity 0.8. So that comes to Px minus 5886 Newton per meter square. So pressure at point C prime marks the interface of oil and mercury. There is this one, interface of oil and mercury. So Pc double prime is equal to Pc prime, that is Pc, that is this much. Then point D, you go to point D in the right limb of the manometer, which is open to atmosphere. So there is free surface of mercury. So the pressure at D is atmospheric. That is when you are expressing pressure as gauge pressure, atmospheric pressure is taken as 0. Now pressure at D is atmospheric, that is 0, that is equal to pressure at C prime minus pressure due to column C prime double D, that is 0.25 meter of mercury, which can be converted to pressure intensity, and ultimately you get Px is equal to 39,240 Newton per meter square or 39.24 kilonewton per meter square gauge positive. So if you want to express the pressure at center line X of the pipe in absolute units, then absolute pressure at X will be atmospheric pressure plus gauge pressure, what we have derived. So 101.3 kilonewton per meter square plus 39.24 kilonewton per meter square, you get 140.54 kilonewton per meter square. So let us go to the next problem. Asked in GATE 2018 with 2 points. So we have a 3 fluid system connected to a vacuum pump. The specific gravity values of the fluids S1 and S2, that is fluid 1 and fluid 2, are given in the figure. So specific gravity of fluid 1 is 0.88 and specific gravity of fluid 2 below fluid 1 is 0.95. So estimate the gauge pressure value up to 2 decimal places of P1, that is at the surface of fluid 1, which is connected to a vacuum pump. See, atmospheric pressure can be taken as 94.53 kilopascals and specific weight of water as 9.81 kilonewton per meter cube. This figure is given, and fluid 3 is water. Now you take AA, that is atmospheric pressure at the free surface of water. So this is free surface, this is free surface. That is given, atmospheric pressure is given. Specific weight of water is given. So specific gravity of fluid 2, specific weight of fluid 2, then similarly specific weight of fluid 1. So the fluid pressure increases with increase in depth at a constant rate equal to the specific weight of fluid. So pressure intensity at the interface BB of fluid 2, this one, the interface of fluid 2 and the fluid 1 is given by PB is equal to PCC plus gamma 1 HCB. So gamma 1 is the specific weight of fluid 1, that is 8632.8 Newton per meter cube, multiplied by, now the total height is say 1.5 and this height is 1, so I want this one, this is 1.5 minus 1, that is 0.5 meter. Then pressure intensity at the surface bottom DD, that is given by PDD is equal to PBB plus specific weight of fluid 2 multiplied by the depth of fluid 2, that is from B to D, that is HBD. So also the pressure at DD can be expressed as PDD is equal to P atmospheric. We can also P atmospheric plus the depth of water, that is 0.5 multiplied by specific weight of water. So that comes to this much. So equating the expressions for PDD. So we have got 2 expressions for the pressure intensity at DD, one starting from surface C through B, and another from the free surface of water in the surrounding tank. So when we equate these two, equation 1 and 2, this is equation 1 and 2, we get P1 is equal to 8731 Newton per meter square gauge negative, or 8.731 kilonewton per meter square gauge negative. So this is another problem which was asked in the preliminary examinations of Indian Engineering Service, Civil Engineering in 2022. A 2-meter wide tank contains water up to a height of 0.5 meter above its base. An immiscible liquid of specific gravity 0.8 is filled on the top of water up to 1 meter height. What is the total pressure on one side of the tank? Take density of water as 1000 kilogram per meter cube and G is equal to 9.81 meter per second square. So pressure at the free surface, that is marked by AA, this is free surface of oil, that is atmospheric pressure. So we will take atmospheric pressure as the datum, that means atmospheric pressure is treated as 0. Now pressure at BB, there is the interface of overlying oil and the underlying water column, that is PAA. So when you are going down, the pressure increases, so plus specific weight of oil multiplied by column of oil, that is 7848 Newton per meter square, that is pressure at the BB. Then pressure at the base, that will be PBB plus pressure due to column of liquid of depth 0.5 meters, that comes to ultimately 12,753 Newton per meter square. So the pressure distribution diagram can be represented like this. So here you have, this is the variation due to the column of oil. Then this pressure at BB due to column of oil will come as a uniform distribution beneath that, where the water column is there, and you have varied pressure due to water column. So you get the pressure distribution. So area of the pressure distribution diagram multiplied by the width of the tank, that is 2 meters, that is perpendicular to the plane of 2 meter wide tank, right? So pressure distribution diagram multiplied by 2 meters will give you the pressure force, that is total pressure on one side of the tank. So pressure intensity at the base of the tank, that is PCC, is this much, that is, the area of the pressure distribution diagram multiplied by the width of the tank will give you the total pressure on one side of the tank. So the area of the pressure distribution diagram comes to 9074.25 Newton per meter multiplied by 2 meters. This is the width. So you get 18148.5 Newton, that is 18.15 kilonewtons. So this is in GATE 2014 in set 2 with 1 mark. This is a question based on the principle of hydrostatic paradox. So we have 3 rigid buckets shown in figures 1, this is 1, this is 2 and 3, of identical heights h, and identical base areas. Further, assume that these 3 buckets have negligible mass and are full of water. The weights of water in these 3 buckets are denoted as W1, W2 and then W3. Also, let the force of water at the base of the bucket be denoted as F1, F2 and then F3. The option giving an accurate description of the system physics is, so we have 4 options. The first option, W2 equal W1 equal W3. So definitely the weight will not be same. They will be different. Okay. And what about the pressure? See, the hydrostatic paradox, see, even though the weights are different, so what is the pressure intensity at the base of each vessel? Pressure is given by specific weight of the liquid multiplied by the column of liquid. Now the column of liquid is same in all the 3 vessels. We have the same liquid in all the 3 vessels. Therefore, the pressure intensity at the base of the vessel having the same column of liquid in all the 3 vessels, it is same. So P is same, the pressure intensity is same. So pressure intensity multiplied by the area of the base. So they have the same area. So identical heights and base areas. So as the base areas are identical for all the 3 vessels, the force that is due to the pressure intensity will be same, that is F1 is equal to F2 is equal to F3. Therefore, this option is not correct. This option is not correct. Now, weights are not same. Weights are different. In fact, this is the biggest vessel and this is the smallest vessel in terms of volume. So weight is equal to what? Specific weight into volume. So here, this vessel, that is vessel shown in figure 2, has the greatest volume. So in fact, volume V2 is greater than V1 is greater than V3. That means W2 is greater than W1 is greater than W3. W2 is greater than W1 is greater than W3. This is all right. And F2 is equal to F1 is equal to F3. So this is the correct option. So you should know how to eliminate the wrong answers. So in all the 3 vessels, even though they have different weights, first they have different weights, but as they have the same column of liquid and also the same liquid, the pressure intensity at the base of the vessel is the same, and as they have the same base area, the pressure force due to the same pressure intensity will be same. That means F2 is equal to F1 is equal to F3. And whereas the weights of water are different, with W2 greater than W1 greater than W3. So the option D is the correct answer. So this is what has been explained. So what I have explained is given here. So even though the base areas and heights of all three containers are identical, as the volumes of the three vessels are not identical, the weights of water in the three containers are not identical. That is, W1 is not equal to W2 is not equal to W3. In fact, considering the different shapes of the three containers, identical base areas and heights of the three containers shown, volume of water in the three containers can be stated as V2 greater than V1 greater than V3. So V2 is the biggest vessel, V3 is the smallest vessel, and V1 is in between. So therefore W2 is greater than W1 is greater than W3. The identical base areas of all containers can be considered as horizontal plane surfaces in contact with water or specific weight gamma. As the heights of water or specific weight gamma over the identical base area are the same, the pressure intensity is uniform equal to gamma H over the base areas A of all the three containers. Hence, the total pressure force due to water exerted on the base area will be, this is gamma A x bar, where x bar is the vertical depth of the centroid of the base area A of each container below the free surface of water in the container. Therefore, as the centroids of all identical base areas of all the three containers are located at the same vertical depth h below the free surface of water, we can write F1 is equal to F2 is equal to F3. Therefore, option D is correct. This is the correct option. So, thank you. So, I hope if you go through all the 5 modules, the 4 modules which I have done some time back, more than a month back, and due to personal reasons and certain things, there was a delay in executing the last module. So some competitive questions asked in competitive examinations like GATE and 1 or 2 questions in the engineering service examinations have been solved, and hope you will master the concept of fluid pressure measurement. Thank you very much.